Hi, this is Marta with Classes for Teens. I'm here today to talk to you about symbols and sets of numbers as part of a pre-algebra review. If you would like to print this handout, which I would recommend that you do, it has linked below. Also, there's a homework set to go with this, which is also linked below. You'll want to try those problems after we've done this class. Okay, first we're going to talk a little about some symbols in mathematics. The first few symbols are listed here. I'm going to give an example of each of those out to the side. The first one is the equal to symbol. The equal to symbol means the same as. So 2 is the same as, or is equal to, 1 plus 1. Okay, so that would be an example of using that symbol. The next symbol, we read these from the left to the right, and the smaller end is on the left, so we call this the less than symbol. So in this particular problem, so many examples we could choose from. 2 is less than 5. This next symbol is less than or equal to. So we could include an example that was just like 2 is less than or equal to 5, because that's also true because 2 is less than 5. Or we could include an example of that symbol using like 5 is less than or equal to 5, because in this case, it's the equal to part that's applicable. 5 is equal to 5. Here, 5 is less than, 2 is less than 5. Okay. The next symbol, again, reading from left to right. This is a greater than. The larger symbol is on the left, and we read from left to right, greater than. So we want to say, if we give an example of that, something like 7 is greater than 3. Okay? Strictly greater than. And this, again, reading from the left to right, the top part gives us the greater than words, and the bottom is the equal to. So this symbol says greater than or equal to. So we could, again, have a problem like 7 is greater than or equal to 3, or we could have 7 is greater than, I'm having trouble writing that. Let's try another one. 3 is greater than or equal to 3. Okay, 3 is equal to 3. Okay, so those are some review of some basic symbols that you've surely encountered before. Let's look at this practice exercise examples that they've given us. We're supposed to choose from the less than, the greater than, or the equal to. Only those three. And fill in these blanks. So these are the same, so I have to use the equal to symbol on those. Going down, 2 is a positive number and that's a negative. So positive numbers are larger. So I point this so that the larger end is facing the larger number. And then I would read this 2 as greater than, going from left to right, greater than -5. Okay, looking at these numbers, the positive numbers over here and the positive numbers are larger. So I put the larger end of the inequality opening to the larger number. And then I read it from left to right. -2 is less than 5. Now the next one is the only one that's really going to give us a little bit of pause for thought. Thinking of your number line, you start with 0 and going to the right, you count 1, 2, 3, and so forth. Okay, I'm going to wear out now. And going to the left, we would say -1, -2, -3, -4, -5. I wanted to go down here to -5. Notice as we go to the right, the numbers are getting larger, and as we're going to the left, the numbers are getting smaller. So if I think about -2 is right there, and -5 is down here. And so the -5 is smaller, it's farther to the left, so it's smaller. So I want the smaller end to point to that. Or we think of this as larger, and we put the larger end there. So reading this, -2 is greater than -5. Okay? And we're going to talk about sets of numbers, and these are easy to forget, but they're important, and they'll come up in math classes over and again, all the way up through pre-calculus. You'll be talking about these, and then after that, you'll be assumed to know them. So you might as well learn these words now, right? So the numbers that we're talking about so far are the real numbers, and you won't really start talking about imaginary or complex numbers, that's the different kind of numbers, until you get to algebra, right? Maybe algebra 2, sometimes at the end of algebra 1. So today we're only talking about real numbers, not imaginary numbers, and they break down into these groups. So over here, I like to start in the very innermost group. These are like nested sets where this little one's inside of that. They're like boxes that you're putting inside of the other. This one's inside of that one, inside of this one, inside of that one, right? These all fit into the others. So these numbers that are in the innermost box are also in the outermost box. So these all kind of go together. The natural numbers, which are also called the counting numbers, start just like you would count. 1, 2, 3, so forth, dot, dot, dot. And you may need to get your own printout of this to see that really clearly. The whole numbers are the same as this, but they also have a 0 in them. The integers are the counting numbers going up. I kind of wish they'd written this differently, so I'm going to do that. It's 0, 1, 2, dot, dot, dot. And then it goes to the left also, -1, -2, dot, 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 that way, okay? I didn't write that really well, but the integers look like counting numbers in the positive direction and counting in the negative direction. So that's the integers. And then we have rational numbers, which is a bigger group. It contains some things that are not in those nested inside groups. Rational numbers has in it the word ratio, which means fraction. So these are numbers that can make fractions. They can look like fractions, 2/3. They can look not exactly like a fraction. Like let's take the number 12. That number is really a rational number because if you put it over 1, right, it's got this invisible denominator of 1. In fact, that number would be down here in the natural number set, but it is also a rational number. So rational numbers can also be terminating, I'm abbreviating that, terminating, ending, decimals. For example, -3.4, it could be positive or negative. That terminates, it ends, it stops at 0.4 stop, right? Or rational numbers can also be non-terminating, which would mean that they go on forever. They do not end. Non-terminating, and abbreviating that, decimals. And non-terminating decimals go on indefinitely, but they have a repeating pattern. Non-terminating, oh, I have to put another word in there. Non-terminating repeating. Okay, so we have one type, and the second type has to be non-terminating and repeating. So if it doesn't end, but it repeats. For example, if you take your calculator and take 2 divided by 3, you're going to see that 2 divided by 3 is 0.66666 forever, and we get tired of that, so we put a line here, and that means repeating 6s. So this is non-terminating. It repeats that forever and ever and ever. That's the non-terminating part. But it does repeat. So that means it's irrational. Now the difference in that and irrational is irrationals are always non-terminating. They don't end, but they're also non-repeating. Okay, so I'm going to write the word terminating in case you need to look at how to spell it. So we have terminating, and here we are talking about non-terminating with the irrational. Notice the word ir means not rational. So these are things that are not rational. They're irrational, not rational. And that's things like pi. Pi is a number 3.14, blah, 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 and it goes on forever and ever. It doesn't end, and it doesn't ever repeat. They've had computers calculating it for, days and weeks and months, right? Years even, and it doesn't ever have a repeating pattern. It just keeps going on, non-ending and not repeating. Some square roots don't work out very nicely, and these are some examples. Those would give us decimals that don't terminate and don't repeat. Now, when you put these on your calculator, for obvious reasons, can't do the decimals going on forever, right? Because the calculator stops at a certain point. And in my calculator, let's see if you can see that. I hope you can. I'm going to take the square root of 10, which was one of the ones they listed. And then I have to put this button right here above the equal sign. Let's see if you can see that. And that's going to make it into a decimal form. Oops, clear. Oops, didn't do that quite right. Let's do it again. Square root of 10. Sometimes I get to looking at the camera and goof up. There we go. And it's kind of close to pi, isn't it? 3.1622. It's an interesting pattern, but it isn't repeating. It just keeps, it went from 2 to 7 to 6. It just keeps going like that. Or you could try like the square root of 5. It's going to be irrational also. And it's 2.236067978. It keeps going, non-terminating, and doesn't repeat a pattern, okay? Unlike something like the square root of 25, some things when you square root them turn out really nice, okay? It's 5.0. That would be, square root of 25 would be rational because it terminates, it ends. Okay, now that we've covered that, let's do a few practice problems. So in this section, they want us to identify each of these and list all of the sets to which the number belongs. So 9, when we look up here, would be one of these counting or natural numbers. So I'm just going to list all these out. It's natural number. It is also going to be a whole number because it's nested inside all of these other boxes, right? It's an integer. It's rational. And one thing I didn't carry on about, and I think I'll do it now, is that the irrational and rational together, rational and irrational, together make a big family of numbers called the real numbers. We mentioned that at the very beginning, but we also need to include that because 9 is a real number also, okay? Now let's do -3. Remember that you can speed the video up, you can stop the video, you can slow it down, you can pause it, do whatever is helpful to you. -3 is not a natural or a whole, it begins in the integer circle. And then the rational, and all of these that we're dealing with so far are real. Okay, now we're going to do 0. 0 is not a counting or natural number, but it begins in the whole numbers. And then we go to integers. I'm going to start abbreviating. Rational, and there are letters for this. Different books use different letters, so I'm not going to use letters to abbreviate this. All right, let's look at the next one, -2.4. Well, it's a negative, which might make you think it's an integer, but those have to be only the countings, and this is a decimal, so that would be irrational, would be the lowest set that's in, right? Okay, so it's irrational, and it's also real. I was saying it is irrational, in case my language got blurry there. This is 1 2/3, which you know if you write as improper fractions, which we'll be doing as part of a review, is the same as equal to 5/3, right? Because you multiply 1 times 3 and then you add the 2 to get 5/3. We'll do that later. That's a rational, it's a ratio. So we'll put rational. And then let's put real. All right, and that brings us to our last example. And this one, maybe you don't know these all on the top of your head, but grab a calculator. It's the 21st century, so we don't mind using these for some things. I have to do this, and it's 645751311. Okay, so it's not making a pattern, and my calculator's cutting it off there, but it isn't ending. It's going to go on forever. So this is going to be irrational. And it's also going to be real. And you probably have done a little with square roots, but square roots are the opposite of squares. If you take 2 squared, you get 2 times 2, which is 4. And if you take 3 squared, you get 3 times 3, which is 9. And notice that 7 is a number that's between 4 and 9. And so these are the only counting numbers, right, that square up. So we know this is somewhere in between, and only decimal numbers are going to be in between that. So when we take the square root, I can predict to get a number between 2 and 3. Let's try it on our calculator just out of curiosity. We did that. We got 2.6, all right, which is what we would predict that it would be between the square root of 4 and between the square root of 9. Okay, so now make sure that you do the homework, which is listed down below, and the answers are included. So after you've worked it, check your answers, and then you'll be ready to move on to the next pre-algebra review. Bye.